Start. So welcome back. We'll have the next speaker, Carlos Raupp from the University of São Paulo, and he will talk about the multi-scale interactions and the diurnal cycle in the tropics.
Okay, thank you very much. I'd like to thank the organizer for the invitation for the present workshop. It's always a pleasure to participate of these workshops on waves, PDEs, right? That André and Paulo and Kranke usually organize. In this talk, I'm going to present a joint work with Pedro Leite Silva Dias, right? That deals with multi-scale interactions and involving the diurnal cycle in the tropics. So, some background informations. In the atmospheric dynamics are basically two different kinds of wave motions, right? So, here the pointer. The low frequency Rossby waves, right, which are quasi-geostrophic, right? Having periods of several days or longer, right? And the inertial gravity waves or Poincaré waves, which are basically, as Esteban spoke this morning, the inertial gravity waves have periods of 1 day and shorter, right? And are associated with deep convective cells, right? So which are directly related to precipitation and deep convection, right? So the Rossby and inertial gravity waves, there exists a large gap, right, in the time frequency spectrum between these modes. So in view of this, many initialization procedures have been performed in numerical models of weather forecast, right, in order to filter out these inertial gravity oscillations, right? So these inertial gravity oscillations are basically considered as a noise in the numerical weather forecast, right? In the mid-latitude context, right, and where the baroclinic instability is the main energy source for the large-scale wave disturbance in the atmosphere, this approach has shown to be reasonable, right? So that this justifies the good skill of the numerical models in the mid-latitudes, right, for weather forecast. But in the tropical region, the main energy source for the wave disturbances is associated with the clouds, right, and deep convections through scale interactions. So that the inertial gravity waves might be important for, the generation of the planetary scale convective coupled tropical disturbance. So an important question that I'm willing to address in this talk is that possible for an inertial gravity wave, a Poincaré wave, to interact with a Rossby mode so as to lead the Rossby mode to undergo significant amplitude modulations, right? So that's the question I'd like to address, right, in this talk. So to address this issue, right, so we need to account for the wave interaction mechanism. So, we know that the waves in general interact through the nonlinear through the nonlinearity of the model, right, of the governing equation. So, for the waves, for the dispersed waves to interact effectively, they must satisfy some kind of resonance relations, right, so that their relative phase, right, do not change with time, right. So this is a necessary condition for the nonlinearity to take place, right. So, as the governing equations in fluid dynamics the nonlinearity in fluid dynamics are quadratic, so the waves must satisfy this tried interaction, this tried resonance synchronization, this tried synchronization relationship, right? In order to for them to significantly interact with each other. So, keep in mind these resonance relations. So, the only way for a Rossby mode, in view of in the context of the atmospheric dynamics, the only way for a Rossby mode to resonantly interact with a Poincaré mode, right? The only way is that one Rossby mode resonate with two inertial gravity waves with nearly equal but opposite time frequency, right? So that they can satisfy this resonance condition for the time frequency, right? So, but as the Rossby mode has a frequency much smaller than the natural gravity waves, so we must have one Rossby mode interact with nearly equal or opposite time frequency Poincare modes. But according to the triad dynamics, there are some energy constraints imposed by the conservation of energy and wave actions, so that in the restaurant triad interactions, the coupling constants and the energy variations are proportional to the individual time frequencies of the modes. So that in this kind of interaction involving one Rossby and 2 Poincare modes, right, the Rossby mode essentially acts as a catalyst component for the energy exchange between 2 Poincare modes. In the sense that the Rossby mode, their energy, the Rossby mode allows the interaction to take place, right, and controls the interaction period of the energy exchange, but its energy or its amplitude does not vary significantly in time, right? And this property justifies somehow the nonlinear Rossby adjustment in mid-latitudes, where the quasi-geostrophic modes evolve independently of the noisy sea of gravity waves, right? Because in the mid-latitude context, if you approximate in a first-order approximation, right, the Rossby modes may be approximated by the geostrophic modes, right, zero frequency modes. So their coupling constants, according to this property, is zero, so that they do not vary. Their amplitude do not vary in time in a triad interaction involving one geostrophic mode and 2 Poincare modes, right? But apart from the nonlinear interaction mechanism, by the interaction through the advective terms, waves in general may also interact through inhomogeneous in the medium they are embedded, such as a variant topography, like a smooth variant topography, right, which is different from random topography, right? In this work, we shall present a new inhomogeneous mechanism through which the two dispersed equatorial wave modes, one Rossby and 1 Poincare mode, may interact through a resonance, right, associated with the variation of the background moisture field in the context of the deep convection parameterizations, right? So the deep convection parameterization refers to account for the net effect of clouds on the large-scale dynamics, right, which corresponds to one of the like a holy grail of tropical meteorology, right? So, the governing equations we adopt, right, is the primitive equations, right, the incompressible equatorial primitive equations, right, represented by a two-layer approximation for the equatorial primitive equations, right? So you have the equations for the barotropic mode and the first baroclinic mode, which is the mode that is mostly excited by deep convection heating, right? So these equations are obtained by a Galerkin truncation of the original Boltzmann-esque equations, right? By considering only the barotropic and the first baroclinic mode, right? And of course, the heating, the forcing is only composed by a first baroclinic heating profile, right? So a deep convection heating, right? Okay. Due to the divergenceless conditions of the barotropic mode, so we can rewrite the equation for the barotropic mode according to this in terms of the stream function, right? By taking the curve of the momentum equation, right, and using the divergenceless condition, right? Okay. In order to construct our linear wave interaction theory, so let's only present the normal modes of the governing equation. So which are the eigensolutions of the linear and unforced problem, right? So by considering the unforced problem and by linearizing the equation, so the barotropic and the first baroclinic modes get uncoupled, right? So the barotropic mode, the eigensolutions of the barotropic mode are associated with trigonometric functions, right? So The eigensolutions are characterized by wave-like solutions propagating the x direction, but without being equatorially trapped, right? So we can, the solutions have an oscillatory structure, you know, with latitudes as well, right? So these modes have a, you know, they are no longer trapped into the equatorial region, right? So they are important. They have a large projection onto the middle and high latitude, so they are important for the tropical impact in the mid-latitude wave dynamics, as well as on the mid-latitude influence on the tropical wave dynamics, right? So, well, as you see that the, you know, the structure of this is an example of one particular eigensolutions of the barotropic mode equation, right? So you can see the global structure of this mode, right? Well, so for the baroclinic mode, right? Due to the presence of the divergence as the divergence is non-zero, right? So the governing equations for the eigensolutions of the associated with the baroclinic mode are governed by this following eigenvector problem, right? So they are described by parabolic cylinder functions, right? So, and these are the famous equatorial trapped wave modes, right? As Matsuno and was the first time pointing out the existence of these solutions, right, in the governing equations of the atmospheric dynamics. So, well, and these waves, the eigensolutions of associated with the baroclinic mode are the Rossby, equatorially trapped Rossby modes, the Poincaré modes, right, the mixed Rossby-Graber waves, or the Yanai waves, right, and the Kelvin modes, right. So the familiar equatorial wave types. Well, the important point in this talk is that there exists a large gap, a large time scale separation between the Rossby and the Poincaré eigenmodes, right? Okay. Well, so just an example of the structure of this equatorial trapped eigenmodes. So here the Rossby modes, which are characterized by a quasi-geostrophic structure, right? And the Poincaré modes, they depart far from geostrophic equilibrium, so they are characterized by a divergent circulation, so you know, associated with deep convective cells, right? Okay. Well, so now let's consider, you know, consider in fact the construction of our linear wave interaction theory through the Diurnal cycle of convection. So let's consider the following parameterization of the forcing term, right? So assuming that the heating is proportional to the lower troposphere moisture convergence, which is one of the first ideas, right, related to the convective parameterizations, right? So it's like the wave-Sisk parameterization, right? You know, where the heat is proportional to the convergence of moisture in the lower troposphere. So by using this parameterization, so here Q represents the background moisture state function, right? So and here the integral Zm represents the lift condensation level or the cloud's base, right? So in this case, the background moisture state function is a prescribed function in our theory, right? So let's set this function in order to roughly represent the structure of the ITCZ, right? As Esteban spoke this morning. So deep convection in a climatological view, right? The deep convection takes place in a very narrow region, right? Surrounding the equator, which is called the intertropical convergence zone, right? So this background moisture state function we call here as the ITCZ function, right? So, well, and we also represent its Diurnal cycle, right? I mean, in order to explore the impact of the Diurnal cycle right? In the wave coupling, right? Well, so Y0 represents is a variable parameter in our theory, right? So they represent the center of the ITCZ, right? Which is related to the seasonal cycle of the ITCZ, right? So it can, of course, it can assume corresponding values between 0 and like 15 degrees north and south, right? And the width of the ITCZ is also a variant parameter in our theory, right? So I'm going to present later, how these parameters influence the theory, the coupling, the wave interaction theory. Well, so the time-dependent part of the ITCZ function is set as a alpha sign, right, during half a day, and 0 otherwise, in order to roughly simulate the diurnal variation of the ITCZ, right? So, and of course, the vertical structure of the force is represented by a deep convection heating, so which only projects onto the first baroclinic vertical mode. Okay, so by substituting the parameterization into the governing equation, we use the following, right? This set of equations for the baroclinic mode, right? So here we have the forcing, the parametric heat forcing, right? And then we can Fourier expand if we Fourier expand the time-dependent part of the heat forcing, we can explore we can analyze the possible resonance involving the diurnal cycle of the ITCZ, right, on the interactions between Rossby and Poincaré modes, right? This table shows the first harmonics of the time-dependent part of the ITCZ function, right? So the first harmonic is the average, the zero frequency, right? So you have the 1 day period and so on. They are multiple, right? But it's very suitable to represent these frequencies of the harmonics of the time-dependent part of the ITCZ function over the dispersion relation of the first baroclinic eigenmodes, right? And if we do this, we can see that the first harmonic of the ITCZ function, right, is close to, which is the 1 day harmonic, right, is close to the frequency of the Poincaré modes, right? So, well, as the Rossby mode has a small eigenfrequency, right? So, it's possible for the Rossby mode resonate with a Poincaré mode through the diurnal cycle of the ITCZ function, right? So, in order to analyze this two-wave interaction, so let's consider the following sats, right? Let's consider a solution with only two modes, a Rossby mode and a eigenfrequency inertial gravity Poincaré wave mode. So, if we consider a solution like this and insert these ansatz into the PDEs, we use the following set of two coupled ODEs, right? So, there is a linear coupling between the Rossby and Poincaré mode through the ITCZ function, right? Due to the presence of the parametric heat forcing. So, these modes interact only if, provided they satisfy the following resonance relations with the diurnal cycle, with one of the harmonics of the ITCZ function, right? Of course, that J must be higher than 0 because, of course, the first harmonic, the zero frequency harmonic, there is no. It's impossible to have a resonance between one Rossby and one Poincaré mode through the zero frequency harmonic, right? So, but through the transient, the transient harmonics, it's possible, right? As we can see right now. So, well, and here the eta represents the coupling constants, right? And, well, if we, use the eigenvalue, eigenvector problem, we can rewrite the coupling constants in a more convenient way, right? So that we can see that the coupling constant associated with the Rossby mode is proportional to the eigenfrequency of the Poincaré mode. And the coupling constant associated with the Poincaré mode is proportional to the eigenfrequency of the Rossby mode, right? So that's, I mean, the most important point of our theory, right? Because it shows that in this kind of interaction, of dual interaction, involve one Rossby and one Poincaré mode through the Diurnal cycle of the ITCZ function, right? The Rossby mode undergoes a much stronger energy modulation than the Poincaré mode, which is not possible in the context of the nonlinear triad interaction, right? Okay. Well, so if we consider a simple case where the Rossby mode amplitude is 0 initially, right? We can address the issue. Well, how can a Rossby mode be excited by a Poincaré mode? So by doing this, right, the analytical solution of this set of two coupled ODEs, right, can be written in terms of the mode's energy according to these two equations, right? So,
why is the wave number of the diurnal forcing 0?
Well, I have set. Well, it's I mean, it's I have set it 0. I mean, in a simplified fashion, right? I mean, to a first approximation, I'm only considering the zonal mean structure of the ITCZ. I mean, I'm not considering the zonal inhomogeneities, right?
Okay, so it's not. I mean, the diurnal forcing filtered by the ITCZ, because if not, I mean, the diurnal forcing has k equals 1 right around the one side of the
No, yeah, but yes, but no, I mean, I'm considering the diurnal forcing of convection, or so it's a result of the diurnal cycle of the solar forcing, right?
Yeah. So it's clear to me that you can take J equals 1 and K. I mean, it wouldn't change much your theory, but there may be some non-zero K.
No, yeah, but I mean, the effect of considering, a zonal inhomogeneity of the ITCZ would be to replace these resonance conditions by a less restrictive one, right? So yeah, but yeah, you're right. Okay, so well, and these equations governing the energy of the modes may be regarded as the parametric equations of an ellipse in phase space, right? I mean, and these equations are valid for the duals involving a Rossby and an eastward propagating natural gravity mode, where the product of the wave frequency is, is negative, right? Because for the case of a random dual composed of a Rossby and a westward propagating Poincaré mode, right? So this product would be positive, and then, these equations, the energies in this case of the modes would grow unbounded in time, right? Being described by hyperbolic functions, right? So this case would be regarded as an instability problem, right? So in this case, we are going to focus on the stable case, right? Where the modes, I mean, the modes exchange energy, but the energies are bounded in time, right? So, okay. Well, so these equations for the wave energies can be regarded as a parametric equation of an ellipse in phase space, where the Rossby amplitude represents the semi-major axis of the ellipse, and the inertial gravity amplitude represents the semi-minor axis of the ellipse, right? And the eccentricity of the ellipse is exactly given by the ratio of the eigenfrequencies, right? By the square root of the ratio of their eigenfrequencies, right? Here in this table we show the possible, some examples of all the possible kinds of resonance. So, for example, here we show one example of two symmetrical about the equator. One example of resonant dual where both Rossby and Poincaré modes are symmetrical about the equator, right? So dual 2 is an example where the Rossby mode is antisymmetrical about the equator and the Poincaré mode is symmetrical about the equator. So dual 3 is an example of where both components, right, are antisymmetrical about the equator, and the last possible type, is given by one Rossby mode, a symmetrical Rossby mode, and an antisymmetric Poincaré mode, right? So here, the first number here, the first index represents the zone wave number, and the meridional, the second one represents the meridional quantum number, right? Which represents the meridional structure of the eigenmodes, right? So the lower the meridional quantum number, the more equatorially trapped the eigenmode will be, right? For all the possible examples, we see that the eccentricity of the ellipse is, the ratio, of the amplitude of the Rossby mode and the amplitude of the Poincaré mode is, near 3, right? So it means that, in this two-wave interaction, right, through the Diurnal cycle of the ITCZ in the context of deep convection parameterization. So the Rossby mode undergoes, if its amplitude is 0 initially, its amplitude will attain 3 times the amplitude of the Poincaré mode, right? So in this kind of interaction, the Rossby mode undergoes a much stronger energy modulation than the Poincaré mode, right? So in order to further explore the impact of the center, of the ITCZ function, as well as its width on the wave interaction mechanism, right? So this picture shows, the interaction period, right? As the interaction period varies with the center of the central position of the ITCZ function, right? The interaction period is a measure of the strength of the interaction, because the stronger the interaction, the shorter the interaction period, right? So this picture shows that, for the possible kinds of duals, right? So this picture shows that in general, right, the interaction is stronger when the ITCZ is located away from the equator, right? And also, the interaction is stronger for dual 4, right? Which is composed of one symmetric Rossby mode and one antisymmetric Poincaré mode, right? Okay, but in general, right? So in general, this picture shows that the interaction is stronger when the ITCZ is located away from the equator. Which is characteristic of extreme seasons like summer and winter, right? So, and this picture shows how the interaction period varies in terms of the width of the ITCZ, right? So, this picture shows that for all the possible resonant duals, right? In general, the interaction is stronger for wider ITCZs, right? We show that as Ry increases, right, the interaction period decreases, so the interaction gets stronger, right? Okay, well, but so far I have shown, the two-wave dynamics. I mean, the two-wave interaction theory, right? The reduced dynamics of, one first baroclinic Rossby and one first baroclinic Poincaré mode, right? But in a more real situation, right, both of these modes can also resonate with, or can also participate of a nonlinear triad interaction with the Barachok wave mode, right? So, in order to represent, to explore in a simplified context, how this, how the nonlinear, how the nonlinear interactions involving multiple slow and fast, waves would be modified by the inclusion of the nonlinearity, right? So, because in a more general picture, right, so this resonance mechanism involve the first baroclinic Rossby and the first baroclinic Poincaré mode involved through the Diurnal cycle of the ITCZ function can compete with the triad resonance, right? So, in order to explore this in a simplified fashion, so let's consider the following ansatz, right, having a solution with 4 modes, so which is composed of a resonant triad coupled to a resonant dual through one of its wave components. So, so let's consider the following ansatz, right, where the stream function of the Barachok component of the flow, so is composed of one Barachok wave mode, and the first baroclinic component is composed of a Rossby mode and 2 Poincaré modes, right? Where the following conditions, resonance conditions, are satisfied. So in these ansatz, we have the following. So the 2 Poincaré modes constitute a resonant triad with the Barachok wave mode, right? And one of the first baroclinic Poincaré mode is coupled to a Rossby mode through the Diurnal cycle of the ITCZ function. That's the simplest scenario. The simplest. Excuse me. Oh, okay, so I'll be right finishing. Okay. Well, so if you insert these ansatz into the PDEs, you can get this reduced dynamics of this 4-wave dynamics, right? So if we perform some numerical computations, we can explore some features of these dynamics, right? So for the ITCZ function centered at the equator, for one kind of the duals, so the interaction is 0, so the dynamics reduce to a single resonant triad interaction, right? But if the ITCZ function is displaced a little farther away from the equator, right? So, we can see the influence of the Rossby mode, of the first baroclinic Rossby mode on the dynamics. So, you can have this kind of period doubling the energy modulations, right? And, one interesting feature about this dynamic is that if we take a longer time integration, so we see that the same solution, right, the same numerical solution, but integrated longer. So the energy of the eigenmodes undergo this longer time period modulations, right? So with something like a decadal time scale modulation. Okay. And if we go even farther away from the equator, right? So the linear interaction mechanism, predominates over the nonlinear interaction. So the solution, gets even closer to 2-wave dynamics, right? So in this case, we have, the linear interaction mechanism competes with the nonlinear resonant triad interaction. So in a more complex dynamics, in a more complex scenario, right? Okay, so, well, I'm gonna finish. Okay.